today's lecture we'll be moving on into same kind of time scale, so really kind of short, kind of 100-year kind of time scale, but instead of looking into the past, we're going to try and look into the future now to see what is in store for us and your children. First of all, just to put kind of the recent climate change into some historical context, we're going to just have a quick look at what the climate's been like to recap what the climate's been like over the past 1,000 years or so. And this, you can't read all of this, it doesn't really matter, but they're basically a whole bunch of different evidences we have for what the climate's been like in the past. But once we go past the instrumental record, once we get past kind of 100 years ago, we have to use proxies. So ice cores, corals, tree rings, things like that. Okay? And that's what is plotted up in this graph here. So now we've got this is kind of now, 21st century, going back 2,000 years into kind of the past. And what we've got here is a whole bunch of series of different proxy reconstructions of temperature. Okay? And the top graph is trying to reconstruct the average northern hemisphere temperature. This graph down here is the average southern hemisphere temperature. Okay, and this is an attempt at reconstructing the global temperature. Okay, and you can see that not all of the proxy records agree. Okay, because they're not direct measurements of the global average temperature. Okay, they're a proxy measurement of some kind of maybe local temperature. So if you're maybe measuring tree rings, you're measuring maybe a combination of temperature and precipitation where that tree grew, and you might build up a regional kind of view of measuring lots and lots of trees. And that might be slightly different to measuring it in a different region or using a slightly different proxy, which is why we have so much scatter, okay, in these data. Okay? But the overall picture is that even if you look at all of the noise in the data over here, okay, this kind of warming at the end here, and the black line is the instrumental temperature record, okay, that is kind of unprecedented in the last 2,000 years. Okay, so we're warmer now than we ever have been. Okay, and this is just kind of like just looking at that instrumental record, just to give you an overview of where some of the data comes from. So these three images of the globe are all the same data set. Okay, so the top data set is the Hadley Centre Climate Research Unit data set for extrapolating global temperatures. This is where we actually have measurements. And what that group does is they just take all of the actual measurements, and they say, we're just going to average those. So obviously if there were, and these are the differences in basically the long-term trend, so the amount of warming we've had since 1900 to 2012. Okay, so you can see most of the globe has warmed. There's a small patch of the North Atlantic which is not warmed, which is kind of interesting. But all they do is they average up all of the measurements. Okay? So that obviously has a little bit of a weakness in that there are some parts of the world that in 1901 no one was measuring the temperature. Okay? So in Africa, no one was measuring the temperature. Some people measure it in South Africa and kind of Kenya and kind of in Egypt, but lots and lots of not measurements. So if there was dramatic climate change that was unusual compared to the rest of the world in Africa, or in South America, or in the Pacific Ocean, that wouldn't be included in the data set. Okay? And these basically is just two other research groups that basically have different ways of trying to extrapolate across these gaps of data. Okay? The important point is that when you do that, so these are basically, and we went through this yesterday, all those different approaches of kind of like different ways of averaging the data, it doesn't matter. Okay? So even though the raw data has got lots of kind of holes in it, okay, it doesn't make any difference really as to how you average it up. We still get this kind of really robust trend of warming over the last century. Okay, so what we do to try and figure out why that warming has happened is, so this graph is kind of slightly complex to understand. So the first thing to note out is that this grey splodge at the bottom, okay, is that climate proxy data. So it's basically averaged together all of those curves that were really, really noisy, and that says that's what the climate is doing. So you can see it's kind of constant, maybe cooling down a little bit towards the 1600s, and then warming. Okay, there's quite a lot of error in that. Okay, and then what this experiment has done is it's taken climate forcings. Okay, so it's taken the climate forcings which we talked about kind of yesterday, which were up here in this diagram here. So you can see with the top graph is the forcing due to volcanic eruptions. Okay, so usually there's no forcing unless there's an actual eruption, and then there's a cooling forcing. So you can see these are negative radiative forcings. Okay, and then at the bottom here we've got another axis. This is the radiative forcing from carbon dioxide mostly, or anthropogenic greenhouse gases. Okay, and you can see that's not happened. Nothing's really happened with that over the last 2,000 years, and then industrial revolution kicked off, and we got this large increase in forcing here. And then the ones in the middle here, these are the changes in the solar flux due to those changes in sunspots, and you can see two different kind of like modes of variability in that. There's the blue line and the pink line. It's kind of browny orange, but anyway, whatever. So that's relatively small. If you just look at the scale here, that's been expanded out compared to the other two. Okay, so this is a relatively small effect. Okay, so, and what kind of the researchers have done here is they ran a whole series of different climate models using those forcings. And they ran two groups of climate models. They ran a series of climate models that only had the natural forcings. Okay, so they only had volcanic emissions and changes in the solar kind of flux. And they ran another group of models that had all three, so included the greenhouse gas changes from anthropogenic emissions. Okay, and that's what the coloured lines are at the bottom here. Okay, and you can see that kind of throughout all of history, all of the history of this graph here, but the last 1,000 years here, all of the models kind of agree with the splodgy data behind. Okay, so it doesn't matter if you include the greenhouse forces or not, we match them. Okay, and the models with the greenhouse gases are the ones with the thick lines, and the models without greenhouse gases are the thin lines. So you can see that it's all good across time until you get to about here, and then the two sets of models start to diverge. Okay, and the models that don't include carbon dioxide greenhouse gas warming start to not explain the data very well. Okay, so this is a line of evidence that says to explain the temperature record, you need to have a model that includes a CO2 rise over the last 150 years. Okay. That in, so this is basically where that warming, where that radiative greenhouse gas forcing is coming from. So you can see we've got most of it is from carbon dioxide. Okay, some of it is from methane, and importantly, so methane doesn't hang around in the atmosphere very long. It does convert into, it oxidizes into CO2 and water. And you can see that those then have a secondary effect. So they, even though you get rid of the methane, you still have this effect from its kind of breakdown products in the atmosphere. So it doesn't completely go away. Similarly with kind of CFCs. And then you have this effect of aerosols, which we went over. So this is like volcanoes going off, but emitted by man. Or people, should we say. People. It's mostly men. So this is another plot of that graph of comparing the model outputs with the climate data. Okay, so this is basically a close-up view of the last 150 years, and the red line are basically all of those different ways of reconstructing global temperature. Okay, so that's what global temperature is doing, and then a bunch of models have been run. Okay, with just the natural forcings, or just the anthropogenic forcings, and in this case they've got the natural forcings, all forcings, and then just the anthropogenic forcings. And you can see that if you just use natural forcings, the model, which is the grey line here, does okay at explaining the data, not great, and then really doesn't explain the last 40 years or so at all. If you just use anthropogenic forcings and you ignore all the natural variability, you do quite well. You do better than the natural forcings, so these match a little bit better, but there are still bits where it doesn't match. Okay? Whereas if you apply all of the forcings, if you basically put everything you know has happened into the model, you obviously do a lot better. Okay? So to explain the recent warming, you need natural forcings and anthropogenic forcings. but you cannot reconstruct it without the anthropogenic forces. Okay, so we can go onto a level of more detail, and so rather than looking at the global average, we can then look at kind of regional changes. Okay, so we can look across different regions of the Earth where we have temperature records that have that we record the temperature through time, and kind of that's what the black curves in each of these plots represents. Okay, and then we can do two sets of models. We can run climate models that only have natural forcings, and then we can also run them that have natural and anthropogenic forcings. So the natural are the blue lines, and in some places it doesn't really matter. So if you look at the sea ice cover in Antarctica, down here at the bottom, it doesn't matter. Our models are not really very sensitive to having anthropogenic forcing. Okay? And that's kind of because there's not really much change going on in Antarctic sea ice at the moment. Okay? But if you look at the Arctic, sea ice, right. If you look at the Arctic sea ice at the top there, you can see that the Arctic sea ice, the black line is descending rapidly. Descending rapidly down here, okay? And the red line follows it, so the anthropogenic forced models do reconstruct that, but the natural models do not. And in almost all regions, okay, the recent climate change, you need the anthropogenic emissions to explain what's going on. I think it's this. Anyway. Okay, so we're going to go on and talk a little about how those models are kind of constructed. Okay, so over the last kind of 20 years or so, there's been lots of advances in the science of producing climate models. Okay, and the way that we used to go about creating those models, we basically come up with some emission scenario. Okay, so basically somebody comes together and says, well, we're going to have 4 scenarios, one where we burn lots and lots of fossil fuels, one where we don't, and then maybe 2 in the middle. Okay? And then someone works out, if we put all of that carbon dioxide and other gases in the atmosphere, what will the radiative forcing be? That's the pink box. Okay? And then that allows us to model the climate, okay, and see what it's like. Okay? And then there's this last box, which is basically mostly social scientists take that model of how the physical climate will change and then say, well, how many people will die, essentially, or how bad will the economy be, those kind of questions. Okay, so we've basically stopped using that kind of linear approach of saying we're going to prescribe how much CO2 we're going to burn in the future. And then we've basically switched it around, and basically now climate models, the starting point is we basically have starting points with set radiative forcings. So how many kind of watts per square metre are we going to change the climate forcing by? Okay, and then we do a climate model, okay, and see how the climate will respond to that overall radiative forcing. And then we take that through a kind of basically a social sciences model that talks to, that basically produces what emissions we will then produce. So that the emission scenario, how much carbon we burn, basically is a product of the modelling, not the input of the modelling. Okay, it's a subtle difference, but it basically means that rather than, it's kind of somewhat philosophical in terms of rather than being forced to, the climate scientists forced to choose what the emissions are. The emissions are basically a product of the modelling. Okay, and these are the kind. This is the table from the old way of doing it. But basically, we have along the top we have a bunch of emission scenarios that have got funny labels. You don't like A1, FB, that kind of stuff. That's not important because they're not called that anymore. But I've got this up here just to show you the kind of things that people think about when you're trying to work out what the global emissions will be. Okay, so it turns out the really important drivers in an economic model of how much CO2 you're going to emit are these guys at the top. So how big the world's population will be, okay, and what the GDP is, how much economic activity we do. Okay, these turn out to be the things that are primarily responsible for CO2 emissions. Okay? So these other things are of secondary importance. They're still important, but you would think it would be nice if we could say, oh, well, we'll just be more energy efficient. Okay, so this is basically energy efficiency per GDP we produce. But actually it turns out that that doesn't really have a big effect. It's much more important that we consider how big the population will be and how big our economy will be. Okay, which is quite controversial, but that's how it is. That's how economics work, unfortunately. Okay, and there's these models then predict how much of different kind of climate gases we burn and how we basically get to the end of the century. So they basically produce these things called emissions curves. So this is the old system. So they basically try and use as an input the CO2 concentration through time into our climate models. And there are some which are basically A1B is the kind of this is the scenario that's commonly used to describe business as usual. That's if we don't make any policy decisions to stop burning fossil fuels. This B1 is kind of like we go full on out for reducing emissions. And in fact, even that's not enough to save the day. Because these are the new, so these are this is the same thing. So it produces for methane. So it's not just carbon dioxide, it also try and model all of the different climate gases, like nitrous oxide. And then you can produce a forcing. Okay, so these are the radiative forcings of those different kind of emission scenarios. Okay, so this is the new way of doing it. Okay, so this is now our starting point of our climate modelling, where we basically say what end point do we want to get to at the end of the century in terms of our radiative forcing. So we want to say our radiative forcing is going to be 8.5 watts more per square metre, 6 watts per square metre more, 4 per square metre more, or 2.6 per square metre more. So those were the starting points. And then basically we go through that process of modelling the climate, modelling the economics, and saying what kind of emissions do we have to produce to get to those final points. Okay. And going through that process, we then also produce essentially what the temperature of the planet will be like under those different kind of pathways of emissions to get to those kind of endpoints by the end of the century. And you can see here that so this graph, so this is basically now. This is the end of the century, okay, and then this is kind of in 300 years' time. That if we choose to do nothing, or basically if we choose to have 8.5 watts per square metre more radiative forcing at the end of the century, which is here, okay, our temperature in 300 years' time will be 8 degrees Celsius more than it is now, which would be catastrophic. If we want to keep below this 2 here, okay, so if we choose this, we choose to have 4.5 watts per square metre more radiative forcing at the end of the century, we might be able to say we'll be just above 2, okay. There's a very small chance that we could be below 2 degrees C. If we want to stay below 2 degrees C, we kind of have to choose this one here, which is we try and have only 2.6 watts per square metre more at the end of the century. We have to choose an emissions scenario that basically does that. You'll notice that this basically flattens out by 2050. This scenario basically involves us stopping burning all fossil fuels by 2050 and developing technology to actively take carbon dioxide out of the atmosphere, which is pretty unlikely. Yeah, so it's not just the average temperature that's going to matter, it's also the spatial distribution. So these are maps of the temperature at basically at different times. So this is on the on this side. This is the average temperature of everywhere at different points on the globe from 2016 to 2035. So this is basically the next kind of like 20 years of your lives. That's here. And these are the different emission scenarios. So this is if we try and go full out and reduce CO2 emissions and all that kind of stuff, we'd be down here. And you see some places are warming more than the others, so the Arctic will warm more than the southern hemisphere. Okay? And you can see there's not much difference by 2035. Doesn't really matter what emission scenario you take, they're all the same. By the end of the century, however, like making a big effort and doing nothing starts to look very, very different. Okay? And also that 8 degrees warmer is not really what matters, because if you look, the continents where people live are actually warming significantly more than the oceans, the rest of the world. So if you look at Africa here, 10 degrees C warmer. Okay, so that's the desert. So that basically means that things like placental mammals, okay, are not going to be able to survive in northern Africa or the central USA. And by placental mammals, I mean that's us, right? So only kind of marsupials will be able to survive those kind of temperatures unless you have air conditioning. So that can be fairly unpleasant. It's not just temperature that's going to change. It's also precipitation. So you can imagine at a first order statement that you put more energy into the atmosphere, it gets hotter, you're going to increase the hydrological cycle. So there'll be more evaporation and therefore more rain. But that's not going to be uniform over the whole globe. Okay, so once again, if we look at the low emission scenarios, so at the end of the century, there's not going to be really much change. There's going to be a little bit more, maybe 10 to 20% more precipitation, kind of globally, not much big spatial differences. If we do no climate action, then you get these really quite dramatic regional differences. You can see some regions, so the Mediterranean. So actually, so to point out that these, the stippling on these diagrams are basically, if you've got dots, that means that what's happened is lots and lots of different models have been run, okay, and they all agree that it's going to be warmer, well, it's all going to be drier over this region, okay. Where you have basically the lines, that the hashing over here, that means that they've run lots and lots of different models and they don't all agree. So it's still quite a lot of uncertainty with these projections. But you can see that some regions are definitely going to get wetter. So the tropics here are going to get wetter. Okay, bits of Africa are going to get wetter. But some regions like Southern Europe are going to get much, much drier. Okay, so lots of forest fires, droughts, that kind of thing. That's all bad. But it's not all about the average temperature in a region or the average aridity in the region. That doesn't really matter so much to us. I mean, if the average temperature of Europe goes up 2 degrees, I don't think anyone would actually notice. Okay? If you go outside and it's like 14 degrees or 16 degrees, not such a big deal. What is a big deal is these extremes of climate. Okay, so we've got, so this is kind of the, up here we've got the, this is the effects of Hurricane Sandy, North America there. There's a heat wave in Paris and over most of Europe, apparently this summer, but I didn't notice that. Flooding events. This is recently in Indonesia, I think, some flooding and obviously drought as well. So basically, when you have an event that's much, much, much wetter or much, much, much drier than usual for the year, that's when basically the infrastructure of kind of human existence starts to not be able to cope. Okay, if it's always kind of going to be warm, if every day is going to be warmer, then it's very easy to adapt to that. But if there's kind of sudden extremes of climate or extremes of weather, that's when most economic damage is done. That's when most people die. Okay, so this is an example from this year. So this heat wave. Okay, so it was only, well, it was up to 5 degrees warmer than a normal July. Okay, and that killed 700 French pensioners, many more hospitalised. It was a big deal. Okay. So if we start to think about these in a kind of a slightly more statistical way, so if you just imagine that example of a heat wave. Okay, so if you imagine in July, in any one year, the hottest or the average, if you just take a heat wave would be 5 hot days in a row. Okay? So if you look at every year that has happened so far, and you look in July and you say, what are the 5, the average of the 5 hottest days? Okay? And you make a number for that, figure out that number for every year. Okay? Every year on average will be around some mean value. Okay? And sometimes the hottest 5 days in July will be a little bit cooler than the year before. Sometimes they'll be a little bit warmer. Okay? But the tendency will be for them to be around the average 5 hottest day in July for any one given year. Okay? Now, if you look at, you'll get a distribution if you do measure lots of different years of something that looks like this, where you're more likely to have something around the average, and it's actually very unlikely for you to have anything that's kind of an extreme cold July or an extreme hot July. Okay? But it's these rare events that only happen frequently. So out here, maybe 2 standard deviations of the variability. It's maybe like 4 in 100 chance. So every 100 years, you might get 4 events that are hot enough to kill 1,000 pensioners. Okay? So we've got to think about what happens if we shift the average state of the climate. Okay? So if we make the climate just a little bit warmer, but keep the same variability, okay, that's what's happening up here. Okay? So this might have been our original distribution, and it's very unlikely that we get down into this region here and happen to have a year where July is really hot and kills lots of people. Okay? But if we just shift the whole distribution, the whole average temperature warmer, okay, that means we have the same variability, so one year might be a bit colder, one year might be a bit warmer, but the likelihood of us exceeding this temperature here for 5 days in a row, whatever it is now a much bigger slice of the pie. Okay? So we've basically increased the likelihood of having an extreme event. Okay? And we've also added the possibility of having a small possibility of having an event that's even hotter than we would have ever expected before. Okay? So we're basically making extreme events more likely and also more likely to be more extreme, just by shifting the distribution of probability of there being kind of the hottest day of the year. So this could be for any kind of extreme event. Okay, so it could be the windiest day, it could be the wettest 12-hour period. Okay, usually the wettest 12-hour period of the year would be around some average for any one year. But as we make the climate wetter, overall, the probability of getting one of these really extreme events starts to go up quite a lot. So it's not just shifting the mean. If we basically make the climate more variable, if we make our weather more unpredictable, okay, this distribution kind of gets wider, okay, as it becomes less certain that any one day will be more like the mean for that time of year. Okay, so if you make the distribution wider, you also increase the probability of getting these extreme events. Okay, so this is happening to the climate system. So if you do both of these things, obviously it gets much, much worse. Okay, so these next graphs are quite hard to comprehend, but they're basically taking that idea of shifting the probability, okay, and basically trying to quantify how much more likely is it for a certain event to happen. So if you look at the one on the left, so this is the time, okay, so this is going into the future, 100 years into the future. And it's basically warm days. So this is basically saying, what's the probability that we will have an extremely warm day? Okay, it's probably got some more specific definition, like what's the probability of having 5 days in a row that are kind of at the top 10% of warm days, using our, the weather over the last 50 years as an average. And you can see over this period, there is a 10% chance, so this is 10, 20, 30, 40, 10% chance that we'll have a warm day that is in the top 10% of warm days. Okay? It's kind of satisfying kind of like a statement there. Okay? But as the climate warms into the future using different emission scenarios. Okay, the likelihood, or the likelihood of us exceeding that temperature of the 10% warm days from the 60s or so, okay, we're much more likely now. So at the end of the century, okay, let's pick even if we're kind of like good boys and girls and we stop burning our CO2, it will be the probability of us having a set of warm days that was at maybe 10%, so one every 10 years, will now be 30%. Okay? And if we do nothing, we do nothing, when I say nothing, we carry on burning fossil fuels, we get to kind of 60%. So that's almost kind of every other year we're going to have a nasty heat wave. Okay? So you can think of it in terms of the likelihood of the likelihood of a hot event happening, or you could also, the graph on the right is the similar kind of argument, but instead of looking at what's the likelihood of an event above some certain threshold happening, it's basically looking at what is the most extreme event that happens in any one year. Okay, so it's basically looking at what is the wettest day. Okay, and as you go through time, we start to get more and more wetter as we go through time. So we can basically do this exercise around the globe and make a map of what is the likely kind of change in the likelihood of something happening. That doesn't really make sense. We want a big one here. So this is basically a map of the return period. So this is basically saying, if we consider a 20-year event, this is basically the wettest day every 20 years. So if you think back through your entire lives and think about what is the wettest day you can remember, okay? And then what this map is showing is how the frequency of that wet day, how is that likely to change? So you can see over in kind of like Africa here, okay, it stays around 20 years, maybe a bit more. Okay? So it means that we're not going to expect it to be getting kind of those extreme 20-year. So basically, the likelihood of there being a 20-year, once every 20-year flood, that will stay the same. But if you look up here in Scotland, okay, we're getting to these blues and these greens. So that's turning into more of a 5 to 7 year return period. So that means that extreme flooding event that might happen over Scotland, instead of happening once every 20 years on average, is going to happen more like once every 5 or 6 years. Okay? So we're just increasing the likelihood of hazardous stuff going on. Okay, so and these are kind of like a summary of those changes. So heavy precipitation events, okay, are likely to increase. You can read through that in your own. Okay, so that's a really important thing about the climate change of the future. It's not just the average change over time; it's the increasing likelihood of extreme events, flooding, heat waves, storms, that kind of thing. Okay, and their increased intensity. Okay, so we're going to talk a little bit now about sea level. So sea level is going up. Okay, so this is the some graphs that we've got at the top. We've got another plot of this temperature over the last 150 years. Okay, you can see that's going up through time. But if you look at the bottom here, you've got the average sea level, and that's going up much more evenly. And that's because that's being largely driven by this excess heat. Okay, in fact, so this is the average sea level going up is actually a much better representation of global warming. Okay, because when you warm the planet up, that heat energy is actually quite a lot of it is being stored in the ocean, causing the ocean to expand. Okay, and you get a little bit of glacier melt and ice sheet melts and things like that. But this is basically a good proxy for the thermal content of the surface Earth, whereas the global average surface temperature, the top one, that's also caused by this kind of global warming, but you also, because it's got a much smaller heat capacity than the ocean, if you start to exchange small amounts of heat relative to the size of the ocean between the ocean and the atmosphere, you get lots of this noise in the system. And that we went through that in the kind of the how El Nino changes global temperatures on a high frequency basis. So sea level is going up. That little red line, little red line. Okay, these are direct satellite measurements of sea level. Okay, so this is kind of very, very accurate and precise. And the dots are a compilation of people that have basically used tide gauges around lots of different places on the world to work out, just watch the sea level, average sea level rise up. Okay, so these are some of the projections that will go into the future. So it looks like by the end of the century we're going to get maybe 0.5 metre of sea level rise. Okay, and it actually looks like it's fairly independent of the emissions scenario. Okay, and that's because there's quite a long lag in terms of the sea level rise and the climate forcing. So basically the sea level rise that we'll get over the rest of the century, the cause of that has already happened. Okay, so the warming that we've had so far will carry on causing the sea to expand. Okay, so it's only once you go off into the very far future that the climate scenario you choose kind of matters. And you can see that this rise is made up of a bunch of components, thermal expansion, glacier melt, and all that kind of, but you can see thermal expansion, the red line, is by far the most important. I should probably point out at the moment that there is quite a lot of controversy in the scientific community about how accurate these projections are. And that controversy surrounds kind of these graphs here. So these basically show that most of the sea level rise over the next 100 years or so will come from just the water warming up and expanding. Okay? But there's starting to become more and more evidence that actually the component from large ice sheets, so the Greenland ice sheet, which is the green line, and the Antarctic ice sheet, the blue line, which are kind of these, well, it's actually these two lines here. Okay, so these are small components at the moment. But as we learn more about how glaciers and ice sheets behave, and this is kind of research that's going quite a lot along in the School of Geosciences here, that actually ice sheets can contribute to, can behave in somewhat unexpected ways and possibly collapse a lot more faster than we thought. Okay, so it's possible that our sea level rise rates could actually be a little bit higher than this. And there are some crazy estimates out there in the literature, up to maybe 2 meters of sea level rise by the end of the century. Okay, but I wouldn't say that there is no scientific consensus about a 2 meter sea level rise. Okay, so, but a meter wouldn't be ridiculous. Okay, so so that's the potential for these guys to collapse rapidly. If you're interested, ice and climate is a good course in geography in the 3rd year or 4th year. And this is just some of the potential impacts of what might happen. I mean, I put images of England here because Scotland's got quite steep sides, so if sea level rises, not a lot happens unless you live in Portobello. Don't live in Portobello for a number of reasons. But I put these up. So London with a 1 to 2 metre sea level rise is pretty much a write-off. So one of the things they're going to do is build a bigger Thames barrage, at a cost of many, many billions of pounds. And this down here is the Dungeness Peninsula, which is a sandy shingle bank and has so this is France over here for scale. So that has a big nuclear power station on it. I mean, why someone thought it would be a good idea to put a nuclear power station there? Perhaps because it was close to France. I don't know. It's just retarded. So that's going to be a bit of a problem for us, or for a independent England. Anyway, so it's not just us, right? So there are all these kind of like other countries as well where sea level rise is a problem. So India, Bangladesh, Shanghai, China. Shanghai is where it's going to be flooded. All the coastlines around kind of the Philippines here are also quite low lying. And I think over half of the world's population live in that red zone. Yeah, so those are the countries that are kind of some of the most populous on Earth, but also people tend to live near the sea. Okay, they live on large mega cities that have built up around trading ports, which happen to be on river deltas, which are very low lying. Okay, so this is a big problem for you. I'll be dead. Anyway, so to summarise this kind of a whole kind of bit about kind of the recent climate change. So really, this is another one of these proxy reconstructions of climate. So really, what we're seeing now, so the red curve is the instrumental record of climate, is really unprecedented over essentially all of human history. Okay, so it is unusual, okay, and bad. And the reason why it's happening is this CO2 increase. So this is the concentration of CO2 back basically as far as we know. We've got longer records now that go to, I think, 800,000 years ago, and carbon dioxide hasn't been above this kind of 300 level for that time. And we're already essentially 400, I think I checked last month, we were at 398 parts per million in the atmosphere. Okay, so that's also unprecedented and bad. And that's where we're going, up there. And there's not a great deal we can do about it. Well, there is. Well, I'll show. So this is the CO2 rising, and you can see that our emissions of CO2 are not really slowing down. Okay, so the Kyoto Agreement was in 1998, I think, and you can clearly see the change in CO2 concentration after that was implemented, right? No. Okay, so this is our basically a graph that's basically made up from accountants counting who's been burning their CO2, right? So this is the problem. Kind of. So since the Industrial Revolution, we've been burning fossil fuels, and some countries have been kind of like, good at reducing their emissions, but whether they've actually done that is, well, so you can kind of see that policy decisions, okay, so policy decisions like having a world war or having the Great Depression in the 1929, early 1930s, those did reduce our emissions, okay? They're not necessarily a good thing, right? The First World War and the Second World War were not, were not an overall win for society, I would say. Defeating the Nazis was good and all that, but it had a short-term effect on our ability to burn fossil fuels. And likewise, you can see other things going on. So the things like the first Gulf War. So it's not actually the first Gulf War, but the one where the US was involved officially. You can see there's a little blip here, and that's because Saddam Hussein decided to burn all of his oil fields. So a policy decision can affect the rate at which we burn CO2, but not a huge amount. You can see the last kind of little blip here where emissions dropped for about half a year was the global financial crisis. So people ran out of money, they stopped making stuff, and we stopped burning fossil fuels. So it's kind of quite interesting here that you can kind of see that China's really taken off, and looks like, ooh, China, you bad boys, you're burning all of that fossil fuels. But the reason why China has expanded so much of its emissions is because these countries down here, Europe, America, they've basically moved all of their manufacturing to China, either actively or inactively. So it's not really China's fault that they're making our stuff for us. You can quite also see, kind of quite interestingly, the collapse of communism in Europe. See, this blue bar here is the amount of carbon dioxide that's being emitted by Russia, basically, mostly, or the Soviet Union. And do you guys know who David Hasselhoff is? Okay, so David Hasselhoff was actually responsible for the fall of communism in Europe, right? Did you know that? So he's a very popular singer in Europe, particularly Germany, and he had an album out in 1987 called Looking for Freedom, and that was played at the time that the Berlin Wall fell down, and they were all singing, like, it was ridiculous. I think big event in European history, and there's David Hasselhoff was standing on the top of an enormous crane singing Looking for Freedom. Okay, and anyway, that happened here, and you can see that the emissions of Russia kind of reduced. The Soviet bloc reduced rapidly after that. Okay, I'd love to say that. I mean, that's a way of reducing your emissions, is to destroy your economy. That's one way that you could think about it, and not necessarily a good way of doing it, but it's one way. But now the next point is a really important point, is that this graph doesn't matter. Because the atmosphere doesn't care what rate you're putting CO2 in the atmosphere. The only thing the atmosphere cares about is how much CO2 is in the atmosphere. Okay? And almost all, well, let's say 2/3 of this carbon is still in the atmosphere. Okay? So the graph that actually matters is this one. Okay? So this is the cumulative emissions of each country through time. Okay? So this, basically, the carbon that we emitted back here, when we kind of were going, yeah, we're the biggest country in the world, our economy is fantastic. That carbon still counts. Okay? So you can see now that China looks like less of the bad guy, and the bad guy is kind of us, the Western world. These kind of things at the bottom, right? The US, Europe. Okay? So, and again, the slightly depressing thing is that, so this graph will never come down unless we actively take CO2 out of the atmosphere. Okay? And it's clearly showing no signs of slowing up. Okay? So that's a fun way to end the lecture and the climate series, but this is kind of, that's the big problem that hopefully some of you as enthusiastic scientists and potentially even kind of like world leaders will solve. So to summarise this lecture, basically we can only explain the recent global warming using climate models that include our anthropogenic forcings. Okay? And importantly, that global warming, you shouldn't just think of it as global warming, think of it as climate change, because it's not just getting warmer, okay? It's also overall getting wetter, but it's not getting wetter everywhere, it's not necessarily getting warmer everywhere, although it will be getting warmer everywhere. It's that the spatial patterns of things are changing, and importantly, the likelihood of extreme kind of economy-destroying, people-killing events is going to change as well. And it's not going to change in a good way. Okay? Sea level will rise, yeah, and it's the total cumulative emissions are the ones that are important. Okay? So it's not China's fault, it's our fault. Okay. Right.